Hi everyone, welcome back to Minute Elements. In this video, we will discuss one of the most beautiful and important properties in trigonometry, which is called law of sine or sine rule. I'm also going to talk about one of the most important historical application of this property. But before we get started, let's quickly revisit some of the interesting observations which we established in the previous video. In the previous video, we discussed sine and cosine functions. We defined these functions with the help of right angle triangle, where sine theta is given by opposite side upon hypotenuse and cos theta is given by adjacent side upon hypotenuse. We also established relationship between these functions and a unit circle, which helped us develop a more intuitive approach to visualize these functions. We observed that for any point B on a unit circle, variation in its y-coordinate follows an oscillating sine function and variation in its x-coordinate follows an oscillating cosine function when point B is moving along the unit circle in anticlockwise direction. We also concluded that magnitude of sine theta and cos theta lies between -1 and +1. So from this discussion, an interesting observation can be developed that trigonometric functions and their properties can be visualized either in relation with triangles or in relation with circle. This fact also has a historical basis. Basically, in ancient times, trigonometry was studied and developed by finding solution to two broad categories of problem. One which involves unknown distances and angles of a triangle and another one related to astronomy, as ancient Greek and Indian astronomers were interested in circle and its properties because they believed planet revolves in circular orbits. Now let's talk about how trigonometry would help solving a problem which involves unknown distances and angles. One of the most simple and elegant application of this is in a process of mapping a geographical area by a method called surveying by triangulation. So let's see how this method works. In this method, three known points are identified which are called as stations. These 3 points are then regarded as vertices of a triangle. Now suppose distance between any 2 points is known and let's call that distance as baseline B. If angle A and C involving baseline B can be measured, then by using sine rule, unknown sides A and C of the triangle can be calculated. Once we know sides A and C of the triangle, then we can identify another point such that an overlapping triangle can be created with side A as a common side. By knowing side A, angle E and D involving side A, we can calculate unknown sides E and D of this new triangle. Now this process is repeated to form a system of triangulation of thousands of such triangles. Now by using such system, an accurate and precise map of a geographical area can be created. One of the historical projects involving this application was the Great Trigonometric Survey of India. This was launched by East India Company in 1802 to accurately map newly acquired territories within India. And this project lasted over a century. One of the biggest highlights of this project was calculating the height of Mount Everest using trigonometry. Here's the map of India developed during this project. If we zoom in, we can see thousands of overlapping triangles formed to map different territories of India. Now, since we know some interesting facts about sine rule, let's get into more detail. Let's start by stating the sine rule. Consider a triangle. Let's say angles of the triangle are named with the capital letters, and sides opposite to each angle is represented by a corresponding small letter. For an example, the side opposite to angle A is represented by a small letter A. Side opposite to angle B is represented by a small letter B, and side opposite to angle C is represented by a small letter C. Then sine rule states that the ratio side A upon sine of angle A is equal to the ratio side B upon sine of angle B, which is equal to the ratio side C upon sine of angle C. Let's develop an intuitive and visual approach to derive sine rule identity using a circle. To do this, we will be using two fundamental properties of a circle. They are inscribed angle property and a property which describes relationship between center angle and inscribed angle of a chord. Let's discuss inscribed angle property. Consider a circle and chord BC. An inscribed angle of the chord BC is an angle subtended by chord BC at any point on the circumference of a circle. Let's call this angle A. Now let's see how this angle A is related to chord BC. According to inscribed angle property, inscribed angles by same chord are equal. Now let's see what does it mean. If we keep chord BC fixed and move point A along the circumference of the circle to various positions, then the angle subtended by chord BC at all these positions will be same as angle A. In this animation, we can see that as point A is moved along the circle, value of inscribed angle at point A by chord BC remains unchanged. Now let's talk about the second property which describes relationship between center angle and inscribed angle. Over here, angle theta subtended at center of the circle by chord BC is called as center angle of chord BC. If angle A is an inscribed angle of chord BC at any point A on the circumference of the circle, then by this property, angle A is equal to half of angle theta. That means inscribed angle is equal to half of center angle. In this animation over here, we can see that value of inscribed angle A is equal to 68 degrees, which is equal to half of the center angle, which has a magnitude 136 degrees. Now let's try to think what will be the inscribed angle of a diameter. That is, if BC represents one of the diameters of the circle, then what will be the value of angle A? Take a pause and try to answer this question on your own. This will help you understand the use of this property. Moving ahead, if we align chord BC along one of the diameters of the circle, then the center angle becomes equal to pi radians or 180 degrees. Therefore, the value of angle A or value of inscribed angle A is equal to half of 180 degrees, which will be 90 degrees. Now let's use these properties and visualize sine rule. Here I have drawn the same triangle again. Let's draw the circumcircle of this triangle by drawing perpendicular bisectors of side B and side A. Let's call the point of intersection as point O. Consider O as a center and distance of point O from one of the vertices as radius, and let's draw a circumcircle. And let's say the diameter of this circle is represented by a small letter d. As we know, sine rule is consisting of three ratios. So let's try to define each ratio individually. To start with the first ratio, which is given by side A upon sine of angle A, let's focus on angle A and side A. Over here, angle A can be imagined as an inscribed angle of chord BC, whose length is given by small letter alphabet A. That means by inscribed angle property, if we keep chord BC fixed and move point A along the circumference of the circle at various positions, then angle subtended by chord BC at all these positions will be same as the original angle A. So let's move point A to a new position A dash such that A dash B lies along one of the diameters of the circle. In this new position, the angle subtended by chord BC at point A dash will be same as the original angle A. Now since A dash B is a diameter and we have seen earlier an angle subtended by a diameter at any point on the circumference of a circle is 90 degree, therefore angle A dash CB will be equal to 90 degrees. That means triangle A dash CB is a right angle triangle. In right angle triangle A dash CB, we can define sine of angle A as BC upon A dash B. We know that length of BC is equal to small letter a and length of A dash B is equal to diameter of the circle, which is represented by small letter d. Therefore, sine A can be given by A upon D. Rearranging these terms, we can write down the ratio side A upon sine A is equal to diameter d of the circumcircle. To define the second ratio in sine rule, that is side B upon sine of angle B, let's consider angle B and side B. Over here, angle B can be imagined as an inscribed angle of a chord AC. That means by keeping chord AC fixed, if we move point B along circumference of the circle to various positions, then angle subtended by chord AC at all these new positions will be same as the original angle B. So let's move point B to a new position B dash such that segment B dash C lies along one of the diameters of the circle. In this new position, angle subtended by diameter B dash C at point A will be 90 degrees. That means triangle B dash AC is a right angle triangle. In this triangle, sine of angle B can be defined as ratio AC upon B dash C, which can also be written as B upon D. Rearranging the terms, we can define the ratio side B upon sine of angle B as equal to D, which is nothing but diameter of the circumcircle. Now, repeating the same exercise by considering angle C and side C, we can say that sine of angle C can be written as C upon D. By rearranging the term, we can write down the third ratio in sine rule, which is nothing but side C upon sine C, which is equal to D, which is the diameter of the circumcircle. Therefore, in triangle ABC, we can say that a ratio side A upon sine of angle A is equal to the ratio side B upon sine of angle B is equal to the ratio side C upon sine of angle C, and all these ratios are equal to diameter D of a circumcircle. This proves the sine rule identity. This identity can be used to develop an interesting and beautiful observation. Imagine what will happen if diameter of circumcircle is unity. If diameter D of circumcircle becomes equal to 1, then for an inscribed triangle ABC, side A, which is opposite to angle A, becomes equal to sine of A. Side B, opposite to angle B, becomes sine of B. Side C, opposite to angle C, becomes sine of C. This is another beautiful way of visualizing sine of an angle. If angle is represented by an inscribed angle A in a circle of diameter unity, then sine of that angle A follows the variation in the corresponding chord BC. So we can graph sine of angle A in an alternate way. Isn't it beautiful? I find it quite fascinating how sine of an angle is related to y coordinate of point B rotating anticlockwise along the unit circle, as we saw in the previous video. And now we saw that it can also be related to chord and its inscribed angle in a circle with diameter unity. So that's it for today's video. I hope you found the explanation intuitive and interesting. Try working out some basic problems on sine rule to make your understanding more stronger, as mathematics is all about practice. In the next video, I will talk about another trigonometric property known as cosine rule. So see you in the next one.